Hello. Welcome to today's discussion of the lever device in the Machine Science Olympiad event. My name is Karen Emmons. I'm accompanied by Ian Emmons. We're both national event supervisors and members of the National Physics Committee. This presentation is particular to the 2026 rules, and it will cover both divisions. So a quick word about the event in total. The event has two scoring parts. There's a written exam, and that's 45% of your overall score. We're not going to be talking about that today. And then there's a device, a hands-on portion, and that's 55% of your score. You're going to use a lever device to measure the mass ratio of pairs of test masses. It's going to be a simple lever in Division B and a compound lever in Division C. So a little bit more detail. The event supervisor is going to give the competitors 3 test masses. Those will be labeled A, B, and C. The competitors won't know the masses of A, B, and C. The object is for the competitors to use their device to accurately measure the mass ratios, the mass of A to B, and then also the mass of B to C. We're not worried about calculating or determining actual masses. You're just measuring those ratios. Competitors are scored based on the accuracy of their 2 ratios, so that's 20% of their total score will be for each one of those 2 ratios, and then how quickly they measured them will be 15% of your total event score. In Division B, the device is a simple Class 1 lever. And the beam on that, the lever part, can measure no longer than 80 centimeters. In Division C, the device is a compound lever, and that's going to be a Class 1 lever connected directly to a Class 2 or Class 3 lever. The connection will be like a flexible or a rigid link, and in this case, each beam can measure no longer than 40 centimeters. In both divisions, competitors cannot use any springs, electric components, or electronic components. No movable masses can be attached to the beams other than just lightweight masses that are just lightweight hooks. We'll talk about the hooks in a bit. And the device must be built to accommodate the masses. Just a quick look at the classes of levers for you to start to see what we're talking about. So a Class 1 lever is what everybody always thinks of as a lever. It's that traditional seesaw with a fulcrum in the middle and a force and a load on one side going back and forth. That's the Division B device, the fulcrum in the middle. The Division C device is one of those attached to a Class 2 or Class 3 lever. And in that case, the fulcrum is on one end of the lever. It's probably really hard to envision at this point what that might look like, but hang in there, we're going to be talking about that in some detail.
So before we get into the details of how to construct one of these devices, I want to talk through what exactly do the competitors do with their device. So we're going to start with the Division B device. And that looks something like this. There's a fulcrum standing on the table that holds up a first-class lever arm. And I should say that for a number of these pictures here, I'm omitting a lot of the construction details. They're sort of idealized pictures, just so we can get a clear idea of what the competitors are doing. So the event supervisor will hand the students a pair of test masses, A and B, and the students will hang those masses on their beam. And of course, at first it won't balance like this. But then the competitors slide the masses along the beam until they do balance. And once the lever arm is level and stationary, then the students will make a couple of measurements, and they'll measure these 2 distances along the top, the distance from the fulcrum to mass A and the distance from the fulcrum to mass B along the lever. And then they take the ratio of those 2 distances, and that is the inverse of the mass ratio that they're looking for. So the mass of A divided by the mass of B is the B distance divided by the A distance. They will write that ratio on the answer sheet as a decimal number, and then they will set aside mass A, and they'll do all of this again with the same mass B and with a mass C that the event supervisor gives them. Okay, so what does this look like in Division C? This is one way to envision a Division C device. You've got the Class 1 lever on the left there in gray, and it's hinged to a Class 2 or 3 lever on the right. The hinge is that red dot in the middle between the two, and you've got one of the masses on the one end and the other mass on the other lever, and you slide them back and forth until it levels out and is stationary. And then they need to measure actually 4 distances, 2 on each lever, and they plug them into this formula here. You can find the derivation of that formula online many places if you're interested where it comes from. But one thing to notice here is that 2 of these distances are from one fulcrum to the hinge and from the other fulcrum to the hinge, and those distances are not going to change. So the students can have them pre-measured and bring those measurements in with them, and then they still only have to measure 2 distances from fulcrums to masses. And just so you can maybe visualize a little better, here's an actual sample device from a website that a competitor many years ago made and gave us permission to include here. And you can see it's very similar to the diagram I just showed. It's got the Class 2 or 3 lever on the right and the Class 1 lever on the left, and the hinge is there in the kind of in the middle. That black thing up above the hinge, just to the left of the hinge, is actually a level that he used to be able to tell exactly when his lever was balanced. Okay, so let's talk about building a practical device. So I've shown you drawings like this that are kind of notional drawings, but they're not really realistic because balancing a beam on a knife edge is just too hard to do in practice. And time counts in the scoring, so your device needs to be very convenient in order for you to be quick. So there's a number of decisions that you face trying to build a practical device, and I'm going to go through those decisions. There's not any one best answer to this, so I'm not going to tell you exactly how to build it, but we're going to talk about the key decision points. So the first one is, what kind of a fulcrum are you going to build? Is it going to be an axle fulcrum or a hanging fulcrum? And I've got some pictures of those here. The one on the left is an axle fulcrum where we drill a hole in the support beam and a matching hole in the lever arm, and then put an axle through them, in this case a bolt going through the 2 holes, and that gives you a fulcrum. On the right is a hanging fulcrum where we've drilled a hole in the lever arm, and then we've got a string that hangs down from a support above and goes through the hole and holds up the lever arm. In either case, the important consideration here is to reduce friction in the fulcrum. You want as little friction as possible. And the hanging fulcrum makes this very easy, but it is a little fiddly to work with, a little bit harder to get everything balanced and so on. And so some people prefer an axle fulcrum, but the axle fulcrum, at least the way I've drawn it here with just a bolt shoved through the 2 holes, has quite a bit of friction. And so if you choose that path, you'll want to reduce that. One good way to do that is to use ball bearings. And an easy source of ball bearings is from inline roller skates. And in fact, the bearings in roller skates wear out pretty regularly. So you can actually buy just the ball bearings for inline roller skates at a sporting goods store or online. Okay, so that's our first decision. Now, a second decision is whether you're going to have movable masses or a movable fulcrum. And I've shown both of those options here. On the left is movable masses. That's just like all the pictures I've shown before, where the fulcrum is fixed in the middle of the lever. That never moves, and the masses slide back and forth along the beam. The other option, the masses are always on the ends of the beam. Usually people put hooks on the ends of the beams for this so that they're always in the exact same spot. And instead, it's the fulcrum moves. The lever arm itself slides back and forth across the fulcrum. The movable fulcrum uses the full beam length, which gives you some more accuracy. But it's trickier to build, and you also have to adjust your computations to account for the asymmetric beam. Because the beam is asymmetric, it actually is exerting its own force, and you have to account for that in the computations. So the movable masses on the left is a little bit easier to build. It's an easier ratio computation, and I should mention that it's really your only realistic option in Division C. You'll see why in a few minutes. Okay, so third decision, what supports the fulcrum? You need a support structure that holds all of this up, because you can't just have the fulcrum hanging in the middle of the air. So, so you need a sturdy structure to hold all this up. And I say a sturdy structure because that makes the device much easier to set up, easier to work with, and that will give you a better time score. So you don't want a flimsy thing. You want something that's really stable. So what kind of materials might you think about for that? Well, for the base, the part that just sits directly on the table, something broad and flat is useful, and a piece of wood, a piece of plywood, or something called MDF, medium density fiberboard. It's kind of like plywood, but it's a very dark brown color. Those all make excellent bases, and they're very easy to drill holes in and screw things to, and so on. For the supports and the lever arms themselves, good choices include wood, meter sticks, which usually are wood, and PVC pipes. PVC is that the material that they make those white plumbing pipes out of, and it turns out that that's actually quite an easy material to work with for building things. And once you've figured out how you want to build your support structure, then you'll also have to think about the particulars of your hardware. What is the fulcrum itself? Is it a bolt? Does it have ball bearings, and so on? We've talked about that a little already. If you want sliding hooks, you don't have to have sliding hooks, because you can just loop the mass loops over your beam if the beam isn't too thick. But lots of people like to have sliding hooks. What are those made out of? One good way to go about choosing your hardware is to just go to the hardware aisle at the hardware store and browse. There are hundreds of products there, and you can let your imagination roam, be a little bit creative, and choose lots of good ways to go about it there. A very easy, cheap way to do hooks, if you want hooks, is to use bent paper clips. You have to make sure that they're sturdy enough, but that's not terribly difficult. And if you want to be a little more sophisticated, 3D printing is an option. You usually can't print the whole device because most 3D printers aren't large enough, but you can use it for brackets and so on that hold everything together.
So let's talk about some of the construction common construction goofs. The one most common goof that we've seen as we've run this event over the years is people making the lever arm too long. It can only be 80 centimeters in Division B, and each of the two lever arms can only be 40 centimeters in Division C. Now, Ian suggested a meter stick as a possible lever arm. It's a great lever arm, but it's too long, right? So you're going to have to sacrifice a meter stick and cut it if you're going to use it in this event. Your device needs to be strong enough for the full ranges of the masses. So this is a problem we've seen. You know, the maximum mass may mass at 800 grams. And I've seen devices just absolutely fall apart when a team puts that heavy of a mass on it. So no paper levers, or, you know, it doesn't have to be really heavy duty materials, you know, but nothing that is flimsy, because you want it to be able to hold that mass. The device also has to handle the maximum mass ratio. What do I mean by that? So the maximum, you have your weights, A, B, and C. You take the one of those that maxes the heaviest, and you divide it by the mass of the one that is the lightest. And that is the maximum ratio. Now, that may not be a ratio that the students are calculating, right? Because they're only calculating A to B and B to C. And what does that mean then? Like, if C is your heaviest and A is the lightest, you're never calculating any ratio between A and C. So this is just the range that they might encounter of the masses at tournament, and that changes based on division and on level of the tournament. Note too that this is not implying necessarily that the mass ratios that the competitors calculate are always going to be greater than 1. You're calculating A to B, and maybe B is heavier than A, so the ratio could be less than 1 or it could be greater than 1. Another common problem that we've seen is devices not being able to accommodate the event supervisor's masses. The masses are very thoroughly described in Rule 4B in the rules, but here's a picture of what our masses look like. So first of all, let's actually take the picture on the right. The mass has to have some kind of a loop hanger, and the loop hanger has to be big enough that a golf ball can fit through that loop. So that's a fairly good-sized loop hanger. Then the maximum height of when you stretch the mass out with its hanger, from its top part to its bottom part can be no taller than 20 centimeters, and then it can be no wider than 15 centimeters. And one common problem we've seen is that sometimes students don't think enough about how tall that is, and the masses don't fit under the lever arms.
They just rest on the table.
Right, and then you can't do the action. So it's important to think about doing that. You also need to think about how are you going to put these masses onto your levers. So one of the things that, Ian was saying, you don't have to use hooks, and you don't have to if you can access both sides of the lever. If you think about the Division B lever that looks like the seesaw, yes, you could just slide, assuming that your lever isn't so thick that it won't go through those hanger loops. You can just slide the masses onto the lever, onto both sides in Division B, and move them back and forth like that. But in C, you can really only access one of the levers that way. You can access the Class 1 lever, but if you recall on the other one that there is a fulcrum on the side that's blocking it, and it's attached to the Class 1 lever, so you can't slide a mass onto that second one. So you're gonna need, in C, you're gonna need at least one hook, and maybe you'll just want hooks on both sides. Some tips. Longer levers are more accurate. So if possible, be close to the maximum length on your levers. And that's particularly true when the ratio is close to 1. And this is another reason why Ian was talking about friction in the fulcrum. If there's a lot of friction in the fulcrum, it's not gonna it's not going to have a lot of movement, particularly if that ratio is close to 1. So good bearings are your friend. A good solution, he talked about the inline roller skate bearings. We saw in the picture of the sample device that they had added a level to the arm. That's a great idea. It makes it a lot easier to judge whether the device is actually hanging level or not. And it's also allowed to put distance markings on the arms of your your levers, to make your measurements faster. So there's nothing that's not disallowed at all. By all means, put distance markings on your lever. And then finally, if you do use hooks, don't forget to account for the mass of your hooks when you're calibrating your device.
Also the mass of a level, if you use
yes,
a level.
Also the mass of the level. Though presumably you have fastened that down to the device, so it's already part of your calibrating, whereas your hooks would be moving back and forth. But yes, and you do have, if you do add a level, you actually have to fasten it, because if you recall early on in the presentation, I said you can't add movable heavy masses, so you can't be moving the level along your lever. Okay, let me try that again. You can't be moving the level along your lever arm. You can only move these lightweight hooks back and forth. Those are the only allowable masses on your lever that you can use. That move. So don't forget to account for the mass of your hooks when you're calibrating. So coming back to this sample device that we looked at earlier, and now that we've had some tips and some construction errors or common things to be concerned about, let's look at this again. You can see on this device that their movable hooks are some kind of a bracket, and then they've added an S hook underneath it, and then they're attaching those loops to that. And it makes me concerned that there's not enough height. It's hard to judge. I can't really tell how tall this one is. It may have been fine in tournament. But if you do something like that where you're attaching the masses partway, already underneath there even further, just make sure there's enough height as you practice. And then you can, as you look at this device, again, you can also see why you need the hooks. If you're doing a Division C device, you can't just slide the masses onto that right-hand lever. Some common execution mistakes that we've seen students do. One thing is sometimes they goof up and they give us the inverse of the answer. So they just need to be clear what the formula is. The event asks for the ratio of A to B and the ratio of B to C. And again, a reminder, in those ratios, either mass may be the heavier one. It's important that the students give an answer as a decimal. This is a new rule this year from previous years of machines. In the past, the answers were allowed to be given as a ratio or as a fraction. Those will not be accepted now. They have to be given in decimal format to a precision that the event supervisor will tell the students. So the event supervisor will tell them if they want an answer to the 10th or the 100th or the 1000th. But so students need to bring their calculators. They need to do the math to write down their answer. And then I can't say this enough, but practice, practice, practice. And they should start learning how to use it without timing themselves. But once they start really getting good with their lever, they need to time themselves to make sure that they can finish in the time. The setup's not quite so bad. They get 5 minutes at regional and 4 minutes at states or nationals. But we've seen many students, once they're handed the masses and they start the device test time, struggle to figure out the mass ratios for both of those mass ratios within the 4 minutes. And usually it just means they're uncertain about how to work their lever. So we can't say it enough. Practice, practice, practice. And practice with masses, again, across that full range, and test it out and calibrate it with ratios across that full range from 1 all the way up to 4 or 5.5 or whatever is allowed at the tournament they're heading to. Thanks for joining us today. As you can see, you have all kinds of options for following Virginia Science Olympiad and the national organization on your favorite social media outlet. We look forward to seeing you all at tournaments this year.